we're now talking about statistical decision theory. So let me call this, because we're so many physicists here, the Schrödinger equation of classification. That's in a loose sense, yeah? So there are no Hamiltonians here. What I want to say is it's the fundamental governing equation. If we've solved this, or if we've understood this, then we've solved our classification problem. It answers the question, what does the very best possible classifier look like? And beyond that, this best possible classifier, how good is that? And the answers to those questions, to honor Bayes, whose theorem I've just shown, are called the Bayes classifier and the Bayes risk. And again, these are technical terms. Now, what we need is first a loss function. Because best possible, always, well, that depends on how you weigh the different kind of errors that one can make. And this loss function has two arguments, namely the true class and the predicted class. And can be summarized in a matrix. So let's say this loss function, if you drill for oil, let's say, then if you drill for oil and nothing was there, it costs you, let's say, $1 million or so, because that's the cost of drilling this single hole. However, what if there had been oil and you have not drilled there, even though you should have? Your company may say that these were billions that you have lost because you didn't drill a hole in the proper spot, but the competitor did. So now you can use this kind of information to weigh your different errors and guide your decisions. Typical is to use the 0-1 loss, which, that's the simplest thing you can imagine. It simply means we pay nothing if we make the correct decision, and we pay 1 unit, $1, €1, 1 something, if we make a wrong decision, no matter which wrong decision. Okay, so in that case, the loss function I have a predicted class and a true class. So if the truth is 0 and I predict 0, I pay 0. If the truth is 1, I predict 1, I pay 0 because I made the right thing. If the truth was 0 and I predicted 1, I have to pay 1 unit. 1 ice cream, $1, 1 something. Okay, and we now want to minimize this loss. So we're going to look at the aim will be to minimize the risk, which is defined as the expected loss. So the risk R of a classifier F is defined as the expectation over all possible features that we could see and all possible classes that we could have of the loss function and the prediction. Now, note that X in this statistical decision theory, X is a random variable. F is a deterministic function. It's your algorithm. Let's say 1 nearest neighbor classification here. The label is again random. The loss function is deterministic. And overall, because we now take the expectation with respect to, so it means we average over the weighted all, we have an average weighting over all possible values. As a consequence, this risk here is also a deterministic function of F. For a given sample. Okay, and assuming a continuous feature space, I can write that as an integration over all of my feature space X. Integral of the expectation of Y of this loss function weighted. So this P of X comes from the definition of the expectation operator. And we now want to minimize this thing at each point in feature space, and it is hence sufficient to just concentrate on the kernel of the integral. So if we want to make the whole expression as small as possible, we want to make it as small as possible everywhere. So we will just look here at this expectation of Y. And we now get a double summation. On the one hand, over all possible labels from my set of labels. And then I need a second variable that can code for the possible decisions that my classifier gives. So that's Z. And then have the loss function. And then I need to pick, this here is an indicator function, or let me write it like this. It's an indicator function that ascertains that my prediction at location x is indeed z. And this weighting here again comes from the definition of the expectation. I have to condition on x because we're doing this computation at location x. So, okay, I hear exhaling. Everybody was happy with the that it makes sense to call this thing a risk. So the loss function tells me how much do I have to pay if the true label was y and if my prediction was f of x. This is the loss. But now in statistical decision theory, we assume that the observation, so the features and the label, they're both random variables. They follow these distributions. And because they're random variables, if I want to know how big this quantity is on average, I will take an expectation of it. So you remember that the expectation is an estimator for the location of a distribution. And if I want to, if I now transform a random variable by taking a deterministic function, so let's say I have some random variable x, and I define a new random variable by taking this function, then I can say that the expectation of z is the expectation of f of x is, in the discrete case, it would be the sum of over all possible values xi. Okay, so this is how I compute the expectation of a transformed random variable. And I'm now interested in the expected loss. So this f is not the same f as on the other slide. This is just, an arbitrary function. This is why I take the expectations of that quantity if I want to know on average how big are the errors that I'm going to have. So I want to know that if I use a given classifier f, and if my samples come from a specific distribution, on average, how many dollars will I have to pay for having made wrong decisions? That was this line here. And, well, that was just using the definition of the expectation operator. So this is the definition of the expectation with respect to x. And down here I said we simply concentrate on this part. Yeah, this is the same. And that was, again, the definition of the expectation operator. And I just wrote this. This was an indicator function. The indicator function is 1 if its argument is true, and 0 otherwise. So this was a way of saying that I take a sum over all the labels that I could observe and take the weighted loss of these. And this extra thing here with the indicator function is just to know which label my classifier predicted. So I'm adding up only the losses for those labels, or for the label Z that was actually my prediction. Plausible or not? Maybe. Go ahead. The example with the coins is... Okay. The example with the coins was not a classification problem. So let me take... I'm trying to remember which supervised learning problem examples I gave. So let's say that I'm again taking a medical example. Let's say that true that the label here. Let's say that the true class would be the question patient should be treated, and let's say that we have a cheap test and an expensive test, and the cheap test, for instance, if it does the right thing, no problem. If my cheap test says that the patient should be treated, and in fact the patient was not sick at all, then I have wasted the patient's time and I have wasted the money for the expensive test. But if, on the other hand, the reverse happened, that my cheap test said, no, the patient need not be treated, but in fact the patient was sick, then the patient may suffer severely and so on because he wasn't treated even though he or she should have. And now it is up to the user to decide how bad is that. So you have missed, or you have not treated a patient even though you should have. How much is that worth to you? How big should the penalty be on that? And let's say if you live in a country where you get sued, like in the US, and the sums can be astronomical, then you want to be very much on the safe side. So let's say the expensive test that you wanted to avoid doing costs $1,000, but on the other hand, if you get sued, you will have to shut down your company and so on. Then you will prefer to be on the safe side and rather have a high false alarm rate than any missed detections. So the loss function is something that the client or the user or the designer has to specify. For example, yeah. The risk we're going to compute. So we put in the loss function. And we put in these densities. And now you're coming to the critical point, because these densities we do not have yet. We need to estimate them from data. But once we have all that, we can compute the risk. And we want to make the risk as small as possible. And for now, I will pretend that these densities, this one and that one, that we know them, which is true for my toy example, which is not true in the wilderness. So there we need to estimate them from data. So to come back to my toy example, the way I proceeded was that I designed these densities by hand, and I sampled the data from those densities. In the real world, it's the other way around. I have a finite training set, and from that I need to estimate those densities. Okay. So we still have it written here for general loss function, but if we just use the 0-1 loss, this can be simplified. Sorry, I now need to refill. So for the 0-1 loss, this can be simplified because L is either 1 or 0. So in this equation here, if this is a summation of many terms, right? My indicator function here lets survive only those terms where it only lets survive the class Z that I predicted. And now in this summation here, if I use that loss function, the only terms that will survive are the wrong predictions. So all Y different from Z. Okay, so I can write this as a summation over all possible Y's except for the class that I have actually predicted. And for all these, the loss will be 1 times P of Y given X. Now, you remember this normalization property. So the sum over all yi's should be 1. And I can use this normalization property because here I have all terms except for a single one. I can use that together with this normalization property to write this in an even simpler form. This is 1 minus P of f of x given x. So the one that you saw here was that one. This one here, by the way, that came from the loss function because we used the 0-1 loss now. Okay? Just to make the distinctions between all those different ones. Okay, so this is the risk at a location X. And we're now just a tiny step away from our result. Namely, we want to make this risk as small as possible. So to minimize the risk, we should predict the class with the highest posterior probability. That is, f of x should be the maximizer or let me write a z here, where z is the different classes, the different labels. So this thing here is the base classifier for the 0-1 loss function. Okay, so that's a beautiful result. It tells us that we should predict the locally dominant class. which is in line with our intuition, I would say. And it tells us that if we do that, this is the best possible strategy there is. So we cannot do better than this. And now we have a couple of buts. So best does not mean perfect. So we have found the best classifier, but this need not have an error rate of 0. There's nothing in our equations that tell us that the risk should be 0. And secondly, it requires knowledge of all the exact densities that enter the equations. And all these exact densities we do not have, but need to estimate them from data. If we work with generative classifiers. But, on the positive side, we found the best achievable classifier altogether. And that's a result I really, really like, I have to say. Now, if you want to read up on this, there is a script on my homepage which is extremely rudimentary. So rudimentary meaning it goes up to chapter 4 and the lecture covers 20 chapters or so. But this part at least is in there. So you can read it up in there. Next week, I'm going to introduce generative classifiers, so ways of estimating the density. And we should fix time that works for you for the exercises. So the point of these exercises is to get hands-on experience with the techniques that we discuss here. And Bernhard will also answer your questions and perhaps give comments on exercises of the previous weeks.